Hello, and welcome to Ready to Derive. In this video, we explore the Intermediate Value Theorem, aka the IVT, a theorem that is very important in proving more advanced results in calculus and beyond. Without divulging too much about it right now, because it will give away the punchline, I can say that this is one of my favorite calculus theorems, because even though the result seems self-evident, it is quite profound. The IVT is an example of an existence theorem, one that can guarantee that an equation is solvable even though it does not deliver a method to get the solution exactly. Without further ado, let's get started.
So let's get a feel for the intermediate value theorem through a scenario. At 1 p.m. you are driving on the highway on cruise control at 65 miles an hour. You encounter some volumes, so you disable cruise control, and then when you resume at 2 p.m. you set it to 55 miles an hour instead because the speed limit has changed. And we are going to explain why you must have been driving at 60 miles per hour at least once between the time 1 p.m. and 2 p.m. And this seems, again, sort of self-evident, but it's pretty profound nonetheless and relies on one very important property of your motion. So let's have a look at this. I always advise you for intermediate value theorem problems to make a sketch of the data points. So you know that at 1 p.m., let's see, at 1 p.m. you were up here at 65 miles an hour. And then at 2 p.m. you were here traveling at 55 miles an hour. So this is speed, and this is time. And the question is, was there a time at which you were traveling at 60 miles an hour? Well, it seems pretty obvious that you can't get from 65 to 55 without actually hitting 60 on the way, unless, of course, the only way this could happen is if you were driving, slowing down, and suddenly, at an instantaneous moment, there was a break in the curve, and you managed to decelerate from, say, 62 to 57 miles an hour in an instant, which is impossible. So the key here is that it's all because our motion is continuous. So you know that when you're driving in the car, that you can that your motion is continuous, so you're going to slow down. Maybe you'll speed up again and then slow down, and maybe you even went less than 55 miles an hour. But the one thing we can guarantee, so what the intermediate value theorem guarantees, is there is at least one time between 1 o'clock and 2 o'clock, here in this graph there are 3 times at which you were traveling 60 miles an hour. Notice what it does not say. What it cannot guarantee is it cannot guarantee that you were ever traveling at 70 miles an hour. So let's put 70 up here. You could have been, you could have slowed down and you could have then sped up and then slowed down to 55 miles an hour. You could have passed 70 miles an hour, but there's no guarantee. The only thing we can guarantee is that any value between 55 and 65, so I could have said, show me that at one time you were traveling 56 miles an hour. If you're traveling 56 miles an hour, let's have a look, since our motion is continuous, we assume our motion is continuous, we know that there was, in this case, just one time at which we were traveling 56 miles an hour. So we can guarantee that there was a time we were traveling between 55 and 65 miles an hour, but we can't say anything about any speeds outside that range. And that's the essence of the IVT. So let's contrast the scenario before with this one. At 1 p.m., Harry Potter is sitting in the Hogshead Inn in Hogsmeade, sipping on butterbeer. At 2 p.m., he is sitting in potions class at Hogwarts. Explain why there's no guarantee that Harry was halfway between the two places between 1 and 2 p.m. So let's start with a graph, as always, of the situation. So we will put time on the x-axis, but this time we'll have distance on the y-axis. And let's choose y equals 0 to be Hogwarts. So the x-axis is when he reaches Hogwarts, and let's have this position be Hogsmeade. And at 1 p.m. he's in Hogsmeade, and at 2 p.m. he's in potions class, which is here. So halfway between the two, let's say that this is halfway, whatever that distance is, why would there be no guarantee that he would pass that halfway mark? Well, the assumption in this case is that is his motion continuous? Well, if he did get on the path, if he did walk the path between Hogsmeade and Hogwarts, of course he at some point would be at that halfway mark. But we know that Harry Potter can disapparate and apparate. So suppose he was in Hogsmeade, he was in the Hogshead Inn, he disapparated, and he suddenly appeared somewhere else in Hogwarts. So in a moment of time, instantaneously, it's sort of hard to know whether it's open circles. They're both open, they're both closed because it happens instantaneously, but he's sort of somewhere in Hogwarts, somewhere near potions class. So at 2 p.m. he makes his way to potions class. So as you can see, the concept of the intermediate value theorem does not apply if the function is not continuous, as is the case for Harry Potter. So now that we have an intuitive idea of the IVT, let's get into the mathematical description. So it all rests on the assumption that a function is continuous on the interval, on a closed interval, AB. So again, to help us, let's kind of just draw this. So here's my closed interval AB. And if it's continuous on that interval, remember from previous definition that it has to be continuous from the left and the right. So that means it takes the value f of a exists, the value f of b exists, and it's continuous on that interval. The next statement is take any number L. So pick a number, any number that's between f of a and f of b. So f of a, right, this is the function f of x. Of course, I didn't label it, but that's the function f of x. F of a would correspond to this y value. All right, so a here, and f of b would correspond to this y value. So this is f of b. All right, so pick a value L in that interval. I might just change colors just to kind of make it stand out. So let's pick a value L anywhere in that interval. And you must ensure that f of a is not equal to f of b. We can explain that a little later, but that's kind of an important caveat. Otherwise, this theorem wouldn't hold. Then there exists a number c in the interval AB. So what interval are we talking about? We are talking about this interval. There is a number c somewhere in this interval such that f of c equals L. Well, again, because the function is continuous, all we need to do is if we just follow, let's go along from L and let's take that down. And yes, of course, there has to be a value c in the interval AB such that f of c equals L. And actually, just to point out that I put ST here, ST is mathematical abbreviation for such that. So that's the statement of the IVT. Once again, just to kind of reinforce, notice that it does not guarantee a value outside of this. So if I chose my L here, if my L was not in the interval f of a to f of b, between those two values, there's no guarantee that my function ever reached up to that value. It could have, but we don't know for sure. So let's look at an example where we can apply the IVT in a situation where we're just looking at a table, so we're not actually examining functions just yet. So the Bay of Fundy in Canada is renowned for having the world's largest tidal variations. And here's a table showing the height of the tide in meters every 4 hours during a 24-hour period. T equals 0 corresponds to midnight. So by employing the IVT, determine any time intervals in which the height of the tide was 4.2 meters during this period. So you will observe that in this case, we are saying that that number L, that magic number L we were talking about in the description of the IVT, in this case, it's 4.2. And so it's sort of, again, you have to assume that the tides are continuous, which I don't think is much, too big of an assumption. And what you're doing is looking for intervals in which 4.2 lies in terms of the height of the tide. And you can see here and here between 4.4 and 5.8, that does not capture 4.2. It's possible that the height was 4.2 in that interval, but we're not entirely sure. But let's look at this interval here. Between 4 a.m. and 8 a.m., the tide went from a height of 5.8 meters to a height of 1.4 meters, and by the IVT, we know that it must have passed 4.2 meters on the way. So if we want to write this formally, it would be good to observe, all right, that h of 4, in this case, h of 4 is 5.8, is greater than L, which in this case is 4.2, which is greater than h of 8, which is 1.4. So that's mathematically expressing what's kind of obvious to us. So because continuity is assumed and because our value of L lies within the desired range, we can say that there exists a time, let's just call it T instead of C this time, in the interval 4 to 8, and that interval, think of that as, it is a time interval. It's between 4 a.m. and 8 a.m. when the height of the tide, so h of t, is actually equal to 4.2. There exists a time, and it may have happened more than one time in that interval, but that's all we can guarantee is the existence of one time. So where else does this happen? So 4 to 8 happens in that interval. And let's see, where else does 4.2 appear between the two numbers? So 4.2 does not appear between 1.4 and 4.1, but it does appear here again. So therefore, in the interval between 12 and 4 p.m. would be another interval. So we could add from 4 to 8, also from 12 to 16 hours, from 12 p.m. to 4 p.m. And then, it goes from 6.2 back down to 1.6. So again, 4.2 is that interval. So we can add on another interval, 16 to 20, between 4 and 8 p.m. And then it's not 4.2 does not appear between 1.6 and 3.5, which is why that interval doesn't count, nor does it appear here. So we have identified the intervals in which we can guarantee that the height of the tide was 4.2 meters at some point within those intervals. So in example 2, we don't really have any context here. This is a classic IVT problem. So let g of x be a continuous function on the closed interval -1 to 4, and we are given the value of g at the endpoints. And as always, we will graph it before kind of diving into the question. So at -1, g is up here at 7, and at 4, g is down here at 2. And we know it's continuous, so let's just make up a function right now to put in there. And then, so let's have a look. Which of the following statements is provable using the IVT? So this problem is designed to kind of root out misconceptions and that are easily made and make sure we know when exactly the IVT can be applied. So let's see, I'll use a different color here. Let's take the first one, A. There is at least one C between 2 and 7 for which GC equals 5. So let's have a look. GC equals 5 is about here. Gosh, it does seem, we know that 5 lies between 2 and 7, but that's the Y value. This is the Y value, or this is the L that lies between the two Y values, 2 and 7. But the C, we know that the C must actually, let me use a different color, must lie actually in the X interval. So C is supposed to be somewhere between -1 and 4. Therefore, we can with confidence say that A is incorrect. So what about the next one? There is at least one C between -1 and 4. At least we're in the right ballpark here. So we know that C has to be between -1 and 4, so these all look like candidates. But now can we guarantee that GC equals 0? So let's have a look. So GC equals 0, well, that's the x-axis. And even just with the diagram I drew, we see that the graph of G never actually touches the x-axis. So there's no guarantee that it reaches 0, and that's because 0 is not in the interval 2 to 7. So let's come up here for one moment and remember that the L value we choose, the only time we can guarantee with the IVT is if that L value lies between 2 and 7. So in B, 0 does not lie in that interval. Now C, there is at least one value for which G of C equals 7. Well, once again, look at the diagram I drew. There's only, in my graph, there's only one point at -1 where the function reaches 7. It is possible, as we've shown before, it is possible that the graph could have popped up to 7. So it could, let's have a look here. We could have done something like this. It could have popped back up to 7 and come down to the value of 2, but there is no guarantee. So once again, because 7, if we see, is not between, remember we need L to be greater than 2 and strictly less than 7, and we can't guarantee that the function will get to 7 again. So the final one, there is at least one C between -1 and 4 for which G of C equals 5. And if we go back up to the diagram, we can see because 5 is in between 2 and 7, we see like that there's actually maybe 3 values at which it achieves a value of 5. So we definitely know that the statement in D is true by the IVT. So in this example, we finally get to see a very powerful application of the IVT. Really its ultimate purpose, which is to establish that certain equations are solvable, even if we don't have the algebraic means to solve them. So we want to show that f of x has at least one 0. The interval is given to us here, but this could also be done even if you don't know the interval. You could go search for intervals where this might be true. What we're trying to establish is that e to the x plus x has a 0, which is in effect saying that this equation is solvable. So here are some little steps to get started. Notice that we don't have the value of f at the endpoint, so we have to start off by finding that. So f of -1, just substituting in, would work out to be 1 over e minus 1. I'm going to try to do this without even using a calculator, just using common sense. And so let's look at the other endpoint, f of 0 equals e to the 0 plus 0, and that equals 1. Now, we need to show that our 0 up here, remember this is L, this is a value, we need to show that it exists between the y values at the endpoints. Now, how do we do this? Well, we don't even have to work out what f of -1 is as a number, because we just need to know that 0 lies in the interval. And if you notice, f of -1, 1 over e would be a kind of very small number, because e is about 2.7 something. So if you subtract 1 from that, that's going to be negative. And f of 0 is equal to 1, which we know is positive. So without actually even getting values for that, we know that 0 must lie in that interval. So let's write it like this. So f of -1, we know that our value of L lies in this interval because we have that this is negative, this is 0, and this is positive. So we can now state the conclusion invoking the IVT, as long as we remember one important thing, is to establish that the function is continuous. So that's the other condition of the IVT. So from a previous video, we learned that all exponential functions and all linear functions are continuous on their domains, and both of them share a domain of -∞ to infinity. And if they individually are, so are the sum of the two functions. So we know that this function f is continuous over all real numbers. So with all that established, we can then state the conclusion. Since f is continuous on -1, 0, and 0 lies between the two endpoints, we can invoke the IVT and conclude that there is a c value in that interval -1, 0 for which f of c equals 0. And what that boils down to is that we have proven that there is a solution to this equation in the interval -1, 0.
And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.